Well, welcome, dynamic students. It's Monday, September 14th. And we have Mark with us and Ryan. That's good. Let's see. We need to maybe do something about this. Let's see. Kind of on a funny slant there. Yeah, that's better. Well, that's not too bad. I wonder, need to move this over. Yeah, that's better. Yeah. Like that. That's not too bad. Let's see who we've got on board here. We have, a good crowd. We've got Megan, Ashley, Ryan, Nicholas, and Mark. I wonder if you guys can hear me. If anybody can hear me, say hello, somebody out there.
Hello.
Hey, good. I guess we're connected. That's good. Well, we have 4 minutes before class. Did you have any questions for me?
I never saw the exam over the past week.
Say that again, please.
The exam, I never saw it on Blackboard.
Oh, you never saw it?
No, I got an email on Saturday. I think there were a couple of us that didn't see it.
What about the rest of you? Did the rest of you see it? Did anybody?
Didn't see it as well.
Well, did anybody see the exam? Hello, anybody out there see the exam? We'll fix this problem. It's not impossible to fix, but I need to know if anybody out there has seen the exam. How about you, Nicholas? Did you see the exam?
No, sir.
That was a no?
No.
Oh,
I
okay.
did not.
What about the homework, Nicholas? Do you get the homework assignments on Blackboard? Can you see those?
Yeah, the homework assignment for number 7 was there, but
Yeah.
the exam never showed up.
Exam never showed up. Well, we might have to have a delayed exam the way things are looking. Was there anyone out there that got the exam? Nobody. What about my friend Ashley? Ashley, you didn't get the exam either.
I didn't.
Well, I don't guess anybody did. How about Braxton?
I did not see the exam.
I don't guess anybody did. Okay. Well, we'll fix that. I'll get in touch with my IT person, who you all know is my 30-year-old daughter. She knows what she's doing with these computers. And so we'll have a delayed exam. It might be delayed a little bit. It's not the end of the world, is it? What about it? Ashley, is it the end of the world?
No.
No, it's not. We'll be okay. How about Ryan? Is it the end of the world, Ryan?
I don't think so.
That's good. I think we'll manage somehow. Well, in the meantime, I thought it was put on there okay, but maybe not. We'll get it on there. Stay tuned. We'll maybe make an announcement, but we'll get it on there. But I say let's go ahead with today's lesson. We don't want to get behind on our academics. I believe today we start this chapter 3.
Yeah.
The
Oh,
exam
that's
just
really
got.
awesome.
Go ahead, I'm listening.
Oh, did you pack?
I'm sorry.
Gotcha. Yeah, I was like, yeah. No, delicious. No.
I'm going to mute everybody, but if you want to unmute and talk to me, you certainly can. Well, I'm going to go ahead with this chapter 13, even though it's not going to be on the exam. The exam's on chapter 12, I believe. But let's look at chapter 13 and let's go ahead. We don't want to get behind in our course. I don't want you guys to be deficient in your knowledge when you go on to OSU or wherever. Now, chapter 13 is Newton's second law. And you've studied that before. Newton's second law. That's the topic of chapter 13. I wonder if you know all three of Newton's laws. The first one was something about a body in motion will continue in motion unless some outside force changes its motion. I think something along those lines. The second law is what we're studying, and it's this one here in mathematical language. F equal ma, and I know you've studied that before. The third law is that one about for every action, there's an equal and opposite reaction. But our topic is the second law, and the joke is N2L, never too late to change your major. But we don't want to do that. We like our major, don't we? Well, let's give you the theory on this. See, this is a vector equation. And so you can write it like this. See, that's the sum of the forces in the x direction. Those are x components. And this is the mass times the x component of your acceleration. Now, if you're dealing with a particle, you don't have to worry about the center of mass, but if you're dealing with a body, then this acceleration is the acceleration of the center of mass. But see, you can break this in 2 dimensions into x and y. We could even break it into 3 dimensions, but let's learn how to work in 2 dimensions first, and then we can worry about 3 dimensions. In 3 dimensions, you really have to get into 3-dimensional vectors. But remember now, we have not only the xy coordinates, but we have normal tangential coordinates, don't we? See, there's your second law in tangential and normal tangential components. Let me ask one of my wonderful students here. Let's pick on, hey, Jesus. Jesus, you're one of my students. I've had you for a couple of semesters. Jesus, what does that little n mean? There's a little n right there, Jesus. Do you see it? Unmute and tell the others what that little n stands for. Go for it. Earth calling Jesus. Earth calling Jesus. Come in, Jesus. He must have left his room or whatever. Let's try my friend Shane. Shane, unmute and tell the group what that little N means there. Go ahead, Shane.
Normal.
Yeah, it means normal. Normal what, Shane?
Acceleration.
Well, yeah, it means normal acceleration. And what does this mean, Shane? This little N here by the F.
Normal force.
Yeah. What I wanted you to say, I think you understand, but that's the normal component of the force. See, this force, it could be a vector. Like here, I'll draw you something. There's a vector. Well, see, it has normal components. Of course, now this would be the X component. Say that's F. This would be the X component, and that would be the Y component. Those are components. See that T there? That's the tangential component. Those little numbers stand for components, and I hope you know how to get those. To get this Fx, for example, what that is F cosine of theta, where this is your theta. It's trigonometry. You have to use trigonometry to get those components. Okay, well, there's one more bit of theory here, and then we'll work some problems. And that's this one here. And let me ask Tyler, unmute and tell the other students what this says here, that F with that little r. What is the name of that, Tyler? Tyler, unmute. Tell us what that little r stands for, Tyler. He's making coffee or something. Stuart, you're not going to let me down. Stuart, unmute and tell the group what that little r is there.
Is it radial?
It's the radial what, Stuart?
Unit vector?
No,
Or
it's not
direction?
it's not the unit vector. There is a radial unit vector, Stuart, and it goes like this. And we'll be using those here in a little while. But that little r stands for what, Stuart? Go ahead, I know you know this.
The radial component?
Yes, it's the radial component of the force. And that little r stands for the radial component of the acceleration. Now, this is a tough one, Stuart, but you can do it. What does that little theta stand for right there, Stuart? Oops. Can you see that?
The transverse component?
Yes, it's the transverse component of the force. And that little guy is the transverse, kind of a fancy name. It's transverse. It's the transverse component of the acceleration. See, the radial transverse coordinate system is what you learned as the polar coordinates. They're just polar coordinates. Now, that right there, I've just really given you the theory in chapter 13 that's important. That's it. You're looking at it. That's the theory in chapter 13. Now, being able to actually utilize that theory, that's what we have to do. We have to know how to use that. So that's what we're going to do in this chapter. So let's pick a problem and let's start working problems. That's enough theory. but being able to use it. What good is it if you can't use it? It's like any other tool, like a hammer or a screwdriver. You know, there's an art to using a tool, like maybe a hammer. You take a little kid, you give them a hammer, they don't know how to use a hammer. There's an art to it. Okay, well, we're going to try some problems now. Now, this first one is, let me make some room here. But there's our theory. We know what we're going to study. We're going to study Newton's second law. And the problem I want to do is F13.2. It's a fundamental problem. But now I need to find it. Hang on. Let me see if I can find it here. If you can find it, sing out and tell me where it is. I'm looking for it. Okay, I found it. All right. A motor exerts a force. Let me write this down here. It has a force of 10t squared plus 100. They're in newtons on a cable, t's in seconds. Find the velocity of the 25 kilogram crate when t equals 4 seconds. You've got this crate here, and it's 25 kilogram. And you're connected to a motor. Now, is there any friction is the question. Let me read the problem here. We're doing fundamental problem 13.2. It's on page 128. Page 128. Coefficients of static and kinetic friction between the crate are mu sub s. Mu sub s is 0.3. Mu sub k is 0.25. You'll notice that mu sub s is always bigger. It's harder to break the static friction and get something moving. Once it's moving, the friction is kinetic friction, and the coefficient is smaller. It's easier. Once you get it moving, it's easier to keep it moving. It's harder to start. Once you get it started, it's not so bad. Now they want to know the velocity at 4 seconds. Okay. Well, now you know the formulas for these things. For instance, the static friction goes like this. I like a little f for my static friction. It goes like this. It's equal to the coefficient, which is 0.3 times the normal. Well, we have to get that normal. You know, the weight is 25 times 9.81. 25, 9.81. Okay, now the weight, take a little room here. The weight here of this is 245.25, and that's going to equal the normal. They should equal, in this case, 245.25 245.25 newtons. And so you can get the frictional force. Well, let me put that in there. Here we go. This is going to be the thing is, though, this frictional force, it's I don't know whether it's going to be static or kinetic. So let me think about that. But if you put that in there and you go 0.3 times that, 0.3 times 245.25, and my calculator says 73.575 newtons. Okay, well, see, when time is 0, when you start the clock, the force is 100 newtons. You know what? That's bigger than 73 newtons, so it's going to take off from the moment you start the clock, because you've overcome the static friction. And once you've overcome the static friction, then the friction is the kinetic friction. You've got to understand something. This really is a less than or equal to equation. When you start, the forces, when you start at time 0, the force is 100. And that's bigger than 73. So you're into static or kinetic friction the minute you begin. So we better do the kinetic friction. Here we go. Now the kinetic friction is 0.25 times the normal. Okay. So instead of 0.3, it's 0.25. 0.25 times 245.25. I'm getting 61.3125. We have just figured out what the friction is. It's kinetic friction, and it's 61.31, run out of room there, 25. Okay. So let's use Newton's second law now. And I need some room here. How about up here? I don't need this anymore. We know we're going to be studying Newton's second law. And the version we want is the sum of the forces in the x direction equals the mass times the acceleration in the x direction. Okay. Well, we got the force. That's what this is. You can put a little x there if you want. But see, say x is going over here to the right. There's our x. And we have it. We just need to divide by 25 kilograms. So let me write that. We have the force. It's 10 t squared plus 100 is equal to 25 kilograms times acceleration in the x. We don't really need the x. We know there's just, this is a one-dimensional problem. Okay. Now that's equal to the mass, which is 25 times acceleration. So we can get an equation for the acceleration now. Okay, I'll make some room here. We don't need those. We know what they are. Just divide by 25 and you can get the acceleration. What's 10 divided by 25? Is that 0.4? I did that in my head. That's kind of dangerous. Take 10 and divide by 25. 10 divided by 25. Yeah, that's right. And 100 divided by 20. Well, that's 4. Guys, I think we just figured out the acceleration. Okay. Now, what do they want to know? They want to know the velocity at 4 seconds. Well, we have an equation that goes like this. Do you guys remember those 4 constant acceleration equations? The trouble is we can't use it. See, this equation only works if the acceleration's a constant. But man, that doesn't look constant to me. See, time isn't a constant. We're all getting older. We don't stay the same, do we? So you can't use that equation. I tell you what you could use. You could use this equation here. That one would be okay. That equation's always good. See that equation there? It's always good. You can put a little happy face over it if you want to. There you go. That equation's good. Well, let's use it. And need some room to use it. There's room here. This will work. How about this? A dt equals dv. So here's your A. dt equals dv. Now can you get to here by plugging in that A, multiplying by the dt? I skipped a step because I'm running out of room here. Maybe I shouldn't skip a step. Let's do it down here. See, this A equals dv dt. You know what that is? That's a what's the word? Definition. That's a definition. But see, you can write it like this. A dt is equal to dv. Can you get from here to here? Can you make it? I know you can't. All I did was I plugged in my A. See, we figured out A is 0.4 t squared plus 4. I plugged it in. A is 0.4 t squared plus 4 dt equals dv. Now, if you can get to here, and if you can see my writing, I think you can. Well, we can make it. Here's what we're going to do. We're going to integrate both sides. And we're going to go from 0 to 4, because that's what they wanted, and from 0 to v, because it started at rest. If you read the problem, I think it starts at rest. Yeah, it says so. Read it. For those of you that just tuned in, we're doing fundamental problem 13.2. It happens to be on page 128, and we're almost done. All we got to do is integrate this. So if you integrate that, you'll get, you'll get 0.4 t cubed over 3, right? Plus 4t. Now you have to plug in these numbers from 0 to 4, but we can do that. And then you'll get v from 0 to 4. Now I'm going to plug in the 4 and see what I get. Here we go. 0.4 times 4 cubed. That's 64, isn't it? I think it is. 64 divided by 3 plus 4 times 4 is 16. I know that for sure. Subtract 0 when you plug in the zeros. And I'm getting 24.53, a bunch of threes, equals V, well, it's equal to 4. No, it's equal to V. No, wait a minute, I'm getting mixed up now. No, this doesn't go from 0 to 4. Some of you could have got a thank you point for that if you'd been awake. It would be V minus 0, just V. That's what it is. And hey, I think we're done. Let's look and see what the answer got. Go with me to fundamental answer F13.2. Let's see if I can find it here. F13.2. They said they didn't get that answer. I did something wrong. The book is usually right. The book is getting, let's see what I did wrong. They're getting V is 14.7 meters a second. Let's see if I can any of you find where I made a mistake? I'm sure they're right. I'm sure they're right. They got a different number here. Okay. Let me stare at this for a little bit here and see what the problem is. Oh, yeah. Let me show you what the problem. Let me show you what the problem is. I treated this as if there's only one force acting on this, and there isn't. There's two. See, this is the force that we did here. I think everything we did there is correct. But here's where I made my mistake, okay? Newton's second law says you take the sum of the forces, not just one of them. And I only took one of them. See, that's only the motor acting on it. I left out the friction. So shame on me. Shame on me. So get rid of all this stuff here. I goofed up. Sometimes I think you guys learn more when I make a mistake than when I just go through and do everything right. We see what I did was I left out an important part of Newton's second law. It's the sum of the forces. That's what that sigma means. So here's what I've got to do. Now this part's still correct. I do still have 10 t squared plus 100. But that's not the only force. I have to subtract that friction. And we know what it is. It's 61 point blah, blah, blah. And then on the right side, we have the mass times the acceleration. Y'all, little Southern talk, y'all see where I made my mistake? You have to use all the forces in Newton's second law, not just some of them. Now let's do this correctly. Now divide through by 25, and what you'll get is 0.4 t squared plus 25 when you divide by 25 into 100. Yeah. No, plus 4. minus, now wait a minute, I've got to take 61. If you have a question here, if you got lost along the way, just unmute and ask, okay? I'm getting 2.4525 equals the acceleration. I bet that's right. And I tell you what, let's do though, let's combine those two, shall we? Let's combine those two and we'll finish off this problem now. And if you take that and subtract it from 4, here's what we have. The acceleration is equal to 0.4 t squared plus 1.5475. Okay. Now, remember I had that integral of a dt equals the integral of dv. Well, let's plug it in and solve it. Here we go. Is there room here? I think so. You have 0.4 t squared 1.5475 dt from 0 to 4 equals, and when you integrate this from 0 to v, you'll just get v. And so now we'll integrate that. And what we'll have is v is 0.4 t cubed over 3 plus 1.5475 t, right? Yeah. But then, see, you have to plug in from 0 to 4. Now we're going to get the answer, I bet. Let's try that. Okay, 0.4 times, well, it'd be 64 divided by 3 plus 1.5475 times 4. Well, I got an answer. I got an answer of 14.72 blah, blah, blah meters a second. Now, I forget what they said the answer was, but let me go back and look again. And what was this, F13.2? I think that's the answer. F13.2, 14.7 is the answer. Yay. The book says 14.7. They just rounded off. It's 14.72 something. Do you have any questions on that fundamental problem 13.2? Okay, well, let me ask you a question then. Let me pick one of my wonderful students here. Let's see. Let me pick on my friend William. William, I never pick on you. Unmute, please. And I want you to answer a question. Are you there, first of all, William? Are you there?
Yeah, I'm here.
Yay, William. William, when I did this problem the first time, I got the wrong answer. Were you watching when I did that?
Yes, I was.
William, tell the crowd what I did wrong. What did I do wrong?
You didn't factor friction into your Newton's second law equation.
That's, William, you stayed awake. I'm proud of you. Good going, William. See, Newton's second law has a summation sign here. That's a fancy Greek letter sigma, and it means to add up all the forces. And I didn't do that. I only had one of the forces, the motor. but there were two forces that were making that thing move. Good going, William. Okay, is there any other comment or question on problem this or whatever we've talked about? Okay.
Now I have a question though.
Yeah.
We were supposed to have a test over the weekend.
Yeah, thanks for asking. Everybody tells me they're having trouble doing that test. And I was looking
I never-
for, yeah, there's a screw up. Now, who am I talking to?
Shane.
Is it Shane?
Yep.
Shane, we're going to fix the problem. I don't know what happened, but I'm going to get my my IT person, and we'll
Okay.
fix it. And we'll have a delayed test. We'll still have a test. It's not the end of the world, but we'll get it to work. I can put an announcement on there for you. But thank you for asking, and you're not the only one. I think everybody had a problem, so we'll fix it. Okay, next we're going to work another problem now. Now this is problem. Let's do 1322. Okay, we are going to do problem 1322, and help me find it. Help me find 1322. I found it. Okay, let me draw. Let's do that. That'll be good for us. Let me draw this. I have trouble drawing these. Okay, come down here. And then I'm doing a pretty good job on this. I think I got lucky. It's coming out okay. I think I need to draw this A a little bigger. Let me draw this one here a little bigger. There's A and there's B. Yeah, that's it. That's not too bad. 50 kilogram block A. Let me make a note of that. And 15 kilogram block B. And they want to know the velocity of the 15 kilogram block B in 2 seconds. Well, I get the feeling that A is going to go down and B is going to go up. I just have a gut feeling about that. And they want to know how fast, what the velocity is of B after 2 seconds, after you release it from rest. Okay, that's the problem. Well, to do these problems, the first thing you have to do is write the dependent motion equation. And we studied that. Dependent motion equation. Now I'm going to shut up for about 60 seconds. And I want you to write the dependent motion equation for this pulley system. And then I'll call on one of you. Go for it. Write it. Well, that's probably 60 seconds, all right. Let me call on my friend here. Let's see. How about my friend Alex? Alex, are you there?
Yeah.
Alex, do you have a dependent motion equation for this pulley system?
Yeah. 3SB plus SA minus SE.
You're doing it the hard way, Alex. What I want to know is I want to have a relationships between the velocity of A and the velocity of B.
Oh,
Did
oh,
you get that far yet, Alex?
oh, VA minus VC plus 3VB.
Now, what did you use? Did you call this one C right here, Alex?
Yeah, it's C,
You could-
right? I think it is.
You could call that C, but Alex, you're doing it the hard way. We don't want to do it the hard way. Did you ever get a relationship between A and B? I mean, just it's either yes or no, Alex. Did you get a
Yeah,
relationship?
no.
You didn't. That's fine. That's what you're here for. Well, let me show you how to do it, Alex, and you're gonna be blessed now. I always say if you knew how to do this, you didn't learn anything. But since you didn't know how to do it, you're going to learn something, and that's good. That's a blessing for you. Now, the book shows you how to do it the way you were doing it. I think you were doing it the hard way, but there's an easy way. See, there's tension in this cable here. And as that cable goes around this frictionless, massless pulley, you have the same tension in that cable there. And as it goes around this frictionless, massless pulley, you have the same tension in that cable there. And as it goes around this frictionless, massless pulley, you have the same tension in that cable there. And if you'll look, you'll see three tensions that are pulling up on B. So you could even write this, that the tension in this strap, that could be a metal strap. It doesn't have to be a movable line or rope or cord. It'll be 3T. You got three tensions on B. So this is going to be 1 VA plus 3 VB equals 0. That is your dependent motion equation. See, you only have one tension on A, but you have three tensions on B. That's it. Now, we're more interested in the acceleration, so we take the derivative of that. Well, the derivative of that is the acceleration of A plus 3 times the acceleration of B equals 0. That's it. That's called the dependent motion equation. It relates A and B. But now you can do it the hard way, and I could go through and it'll take me about 15 minutes to add up all those distances, but you'll come up with the same equation. There's actually a third way. If there's only one movable rope, you just count the ropes. There's 3 ropes on B and only 1 rope on A, so it's 1A plus 3AB. Okay, well, we're not done yet. They want to know what the velocity is of B after 2 seconds. Well, that's where Newton's law comes in. In this case, we're going to write the sum of the forces in the y direction equals ma in the y direction. Now, we'll just say y direction is positive going down. That's okay. We can put y going down if we want. That's fine. Okay, and so what we have to do is we have to write the equations, Newton's second law equations. See, that's what this is. This is Newton's this is Newton's second law. That's what it is. And we don't want to forget, like I did last time, and just put one of the forces. We want to, in this case, have all the forces on our bodies. So it might help if I draw the bodies separately. See, do I have room over here? I have room. Here's B. And you know what you got? You got 3 T's going up on B. All right? There's your 3 T's. 3 T's going up on B. Can you read my writing? I need to write better. There's your 3 T's. Now you also have this weight here. And the weight is 15 times 9.81. Let me find out what that is. 15 times 9.81. I'm getting 147.5 newtons. So see, we could write the equation. Now we think B is going up. So we got 3T minus 147.5 newtons equals the mass, 15 kilograms, times the acceleration of B. I just wrote Newton's second law. That's it. That was Newton's second law for B. Now I'm going to do A. Okay. Well, on A, I just have one tension going up, but I've got 50 times 9.81 newtons going down. Let me see what that is. 50 times 9.81. I'm getting 490.5 newtons going down. Okay. Now I'm going to write that equation. Now here's where I'm getting mixed up. I said going down was positive, so I think I wrote these backwards. Let me write them the way I had them. This should be 147.5. Going down, I said was positive, so let me do it that way. And the 3T going up is negative. So there's my Newton's second law. And I'm writing everything going down as being positive. Now I'm going to do the same thing with this body A. Only it's got 490.5 newtons going down and only one tension going up. And here's its mass. And there's its acceleration. Hey, I've just written the Newton's second law equation for body B. Let me box these all up for you. This is the Newton's second law equation for body B. This is the Newton's second law equation for body A. You know what? We have 3 unknowns. We don't know what tension. Let me write them for you. The unknowns are tension. We don't know the tension. Acceleration of B, we don't know that. Acceleration of A, we don't know that. We have 3 unknowns. However, we have 3 equations. 3 equations and 3 unknowns, so it's doable. It's just a matter of algebra, I guess. We can do that. Tell you what, let's do. You might have your own preferred way of doing that algebra. So, some of you like to do the 3x3 matrix, you know, that you learn in algebra, or you can do substitution. I'm going to do a combination of substitution and just elimination, I think they might call it. See, the acceleration of A could be written as negative 3AB. Can you get from here to here, algebra students? I know you can do it. Okay, and then what I'm going to do is I'm going to rewrite these equations. I'm just going to rewrite this one, 147. I'm doing algebra now. This is not dynamics. This is algebra. All I did was I rewrote this equation. But now in this equation, I'm going to substitute that. So here goes. I'm substituting now. 490.5 minus t equals 50 times a minus 3ab. See, what I did was I substituted acceleration of A is negative 3ab. I just substituted it in there. I wrote this equation underneath here. But now I have two equations and two unknowns. Anybody got lost on that? Speak up. Well, if you're not lost, then the next thing I'm going to do is I think I'm going to divide this first equation. I think I'm going to divide it all by 3. Now, if you do that, here we go. I'm going to divide, and there's more than one way to do this. It's just a matter of solving some algebra here. 147.5 divided by 3 is 49.166. And see, when you divide by 3, you'll just get t. And when you divide this by 3, I think you'll just get minus 50. No, you'll get 5. There we go. What I did was I took this equation and I divided by 3. That's legal. See, I divided that by 3, I divided that by 3, and I divided that by 3. Now, wait a minute, now I'm getting mixed up. No, I'm not. No, I'm not. I'm not mixed up. I don't think I need this equation anymore. Just forget it. Now you see these two equations? I'm almost done. I'm going to subtract. If they're equal, I can subtract equals from equals. And here's what I'll get. Is there room? Not much. I think I can squeeze it in right in here, though. I'm going to subtract 49 from the 490. So here goes 490.5. I'm going to subtract 49.166. And here's what I'm getting so far. I'm getting 441 point, probably a bunch of 3s is what it amounts to. But the beauty is when you subtract those, you get nothing. Now here, you know what that is? That's minus 150. And when you subtract 5 from minus 150, I think you get minus 155 AB. So now I can solve for AB. Here goes. AB is equal to, divide that into that. Divide that by 155. I'm getting a negative 2.847, what is it, meters per second. AB. Hey, what does the negative mean? Well, if going down is plus, negative means it's going up. See, B should be going up at the end of 4 seconds, that is, right? Did we do this at 4 seconds? Now I'm getting confused. What we, no, at 2 seconds, at the end of 2 seconds. Oh, we haven't done the velocity yet. all we've got is the acceleration. Do I have room down here? Yeah. Now here, to get your velocity, and these are constants. So you get to use this equation here. See, the forces are all constant, they're not changing. The accelerations are constants, they're not changing. It starts at rest. So if you're doing B, you're just going to have the 2.847 meters, and that's meters per second squared. Somebody could have gotten a thank you point just now. Meters per second squared times 2 seconds. This should be our answer. Okay, I'm going to multiply by 2. I'm getting 5.695 meters a second going up. Well, that should be the answer. Let's look and see if it is. I goofed up on the last problem. Let's see if I did this one right. This is 1322, and I'm looking for the answer now. This is 1322, okay. 1322, they said 5.70 meters a second. Well, they rounded off. The book, does that show up? Yeah, it shows up. The book got 5.70. Is that what I just said? 1322? Yeah, 5.70 meters a second. Well, look, they just rounded off. We got 5.695. They did okay. We did okay. We use Newton's second law. Do you have any questions on problem 1322?
I have a question.
Yes.
In your velocity equation, why is your acceleration positive?
Good question. Is that my friend? Identify yourself, please.
Ashley?
Ashley. Ashley wants to know why I had a positive there. Of course, Ashley, you know this is 0. It doesn't have any initial. So whatever the velocity is the acceleration times the time. Now we're doing B, and we know B is going up because A is going down. And we should have, Ashley, we should have a negative. If going up is negative, according to our stuff there, you know what the book did? They just gave you an absolute value, Ashley, of how,
Okay.
yeah, how fast it's going. But we said going down is plus. We could have said going up is plus. It would have been fine. But thanks for asking. Anybody else? We're talking about 1322. Okay, well, let's do another one then. That was fun. Are you sure? Are you all sure? Anybody else have a comment or question? Well, okay. Here's your chance. I'm going to erase this. We're going to say goodbye to 1322, and I'll get on my phone to my IT person. I might do that here in just a minute. I'll get you started on something, and I'll go get my phone. I think I left it downstairs there. Okay, well, goodbye, 1322. We are studying Newton's second law. And this one here is, this is problem 13.5. Let me find it here. Yeah, here we go. This is 13.5. Now we have a hill here, a 30-degree hill. It's sort of like that. There you go. It's a 30-degree hill, and we have two crates, looks like. We have a big, heavy crate and a smaller one. Let me write this down. Now, this is 13.5. It's on page 129. And we have, this one's A, this one's B. But they're connected by a metal connection there. They just call it a link, some kind of metal link there that connects them. But now there's friction. And they said they're, these are the coefficients of kinetic friction, because it's sliding. It's sliding down the hill. And the coefficient of kinetic friction for A is 0.1. And the coefficient of kinetic friction for B is 0.3. You know what that means? It means B has a rougher surface on it, and A is more slick. See, A has a smoother surface. And I think what's happening is B is acting as a brake on A. A would go down the hill a lot faster if it weren't for B. So you see this metal link here? You know what it's doing? It's pushing up on A and trying to slow A down. But it's doing the opposite on B. B would go slowly down the hill, but A is pushing on it, this heavy body A. And so that link is a compression. It's got compression in that link. It's pushing. See, the way it works is compression pushes and tension pulls. Let me write that. Compression pushes and tension pulls. Like, for instance, if you want to take your dog for a walk, or in my case, if my dog wants to take me for a walk, I'm holding on to my dog's leash and she's pulling me down the street because it's got tension in the leash. See, tension pulls. The dog's pulling. Of course, I'm pulling back. I'm pulling back on her leash, and she's pulling me, and tension pulls. And the thing about a dog's leash, you can't do compression. If I try to push my dog down the street with the leash, it doesn't work too well. See, ropes and cords and dogs' leashes don't push very good, because when you push on a leash, it just sort of collapses. They do good under tension. You can pull, but you can't push very good. So you understand that. Well, let me read this. Blocks A and B are 10 grams and 6 grams. Let me write that. This is 10 kilograms. And this is 6 kilograms. They're released from rest, is that right? I don't know, let me read it, please. They're released. I get the feeling from rest. Determine the force developed in the link. Okay, we'll do that. Yeah, we got all the info. Okay. Well, the way you do these problems is you put all the forces, get yourself a red pencil or pen and put all the forces on it. Now see, this has a compressive force that's pushing on it from the metal link, and it has a weight of gravity, and it also has a normal force. And I don't want to forget the frictional force. Look at there. There are 4 forces acting on that small body, B. Now on this one, there's a force on it pushing. Remember, it's compressive. Of course, it's going to equal this compressive force here. And it has a weight. Hey, I can do that weight in my head. 10 kilograms times 9.81. You know what that is? That's 98.1 newtons is the weight. Now this weight here is a little different. Let me see what 6 times 9.81 is. 6 times 9.81. I got 58.86. Okay, 58. This one's 58.86 newtons. Oh, wait a minute, I don't want to forget the normal force. Now, a normal force, what that is, they use a Greek letter, eta. Alpha, beta, gamma, delta. Alpha, beta, gamma, delta. Zeta, eta. Alpha, beta, gamma, delta, zeta, eta, theta. Yeah, it's eta. It's a Greek letter eta, and it's perpendicular. See, that's what normal means. Normal means perpendicular. See, this is perpendicular to the surface there. Okay. Now we know what these weights are, and we can get these normal forces because in the y direction, call this direction here the y direction. The sum of the forces in the y direction is 0 because it doesn't accelerate in the y direction. Only, we're going to call this the x direction. It accelerates in the x direction, but not in the y direction. And so in the y direction, you can write, on this body, you can write 98.1 newtons going down. I guess in the y direction, that'd be a minus, wouldn't it? And it'd be a plus the, well, no, wait a minute, it's cosine of 30. So you want the component in the y direction. So you'd have to take cosine of 30. It's negative going in the negative y plus the eta, and you get 0. Okay, so we can get that normal force. It will be 98.1 times cosine of 30. Did you get this normal force as 84.957 newtons? Hey, you can get this normal force here too. It's the same deal. It'll be the sum of the forces in the y direction will be 0 on body B. And it'll be minus 58.86 cosine of 30 plus the eta on B. See, that's the eta on A. And so that's 0. And so that is 58.6 times cosine of 30. Well, I'm getting a eta. It's a Greek letter eta, ETA. Eta. I'm getting a value of 50.749 newtons on the normal force on B. Now we can get the frictional forces. Whoops, I forgot to draw my frictional force. Shame on me. There's 4 forces on each body. See, that has a frictional force. And the way to get it is you take, in this case, you take 0.1 times the normal. Well, that makes that friction 8.495 newtons. And this friction here, see that friction there, that's 0.3 times the normal, which gives you 15.225 newtons. Okay, so now we have all our forces and we can write our Newton's second law. This is how you do problems. You draw your bodies with all the forces in red. You try to find the forces, and then you write your Newton's second law. Now what I want you to do, I'm going to shut up for a minute. I want you to write the Newton's second law for body A and for body B. And after you do that, I will write it and we'll compare and we'll see if you got it right. Okay, I'll be quiet. I want to see if you can write the Newton's second law for body A. Now there's 4 forces. Go ahead. While you're doing that, I'm going to go get my cell phone so I can call my IT person. Hey, all of my students in my dynamics class say that they cannot pull up their exam 1. They're able to pull up their homework assignments okay, and they were supposed to be available last Wednesday, and it was supposed to be due last night, but none of them. Yeah, take a look at that. Okay, meanwhile, I'm going to go ahead with my class here. I'll just put you on speakerphone. Okay, well, yeah, maybe I shouldn't put you on speakerphone. Too much noise there. I'll take you off of speakerphone. But I've got you right here. Okay, let me put the answers up here and let's compare. We have 5 minutes left and we can solve this problem. Okay, on A, we're really just interested in the sum of the forces going down in the x direction. So we don't care about the normal. But see, the x direction is going down this way. So what you've got here is a component. See this 98.1? It's got a component in the x direction, and what it is 98.1 newtons sine of 30 going down the hill. And then you have the friction, which we know is 8.495 newtons. But see, it's going in the opposite x direction. And then you also have this link force. I don't know what to call it. Let's just call it the force of the link. How's that? It's not equal to 0. It's equal to the mass of that, what is it, 10 kilograms times the acceleration in the x. That's it. Is that what you had for body A? Now I'm going to do body B. Do I have enough room? Yeah, I have enough room. Here we go. We're going to take all the forces in the x direction. And what that will be is 58.86 newtons. But see, we just want this component that's going down the hill. We're doing the x direction. So it's sine of 30 minus the friction. Well, see, the friction's going up the hill. It's 15.22. Yeah, I'm listening.
And available until 9/12. Did you want me to extend it?
Well, it says it was available till 9/12. What is today, the 14th? Yeah, let's extend it. Give them a couple of days.
Okay, so 9, what, tomorrow maybe? 9:15?
Well, they haven't even started on it yet. But you could give them till tomorrow at midnight. How's that?
Yeah.
That ought to work. What will that be? The 15th?
Yeah, and then hang on just a second. Is there somebody that you check and see if it posted?
I'll tell you what, give them to the 16th. I'm worried about them. I want them to do well on this. Yeah, okay. Earth calling anybody out there in my class. My IT person is going to change this to, you should be able to get that exam 1 till midnight on the 16th. What's that, Wednesday?
Yeah, can you ask them if they can see it?
Yeah, hey guys, anybody out there, can you see it? The exam 1?
Yeah,
can
there's
see it.
Yeah, the exam just popped up.
Oh, it popped. They said yes. It popped up. I think it's going to work. So they've got till midnight Wednesday night, right?
Yeah, the 16th.
Hey, thank you so very, very much. And the class thanks you. Hey, everybody, say thank you to my IT person.
Thank you.
Thank you.
Thank you.
Thank you.
You're welcome.
Okay, buddy. Talk to you later. Bye.
Bye.
Bye-bye. Yeah, it's nice to have an IT person. Okay, now let's finish this off. We only have 2 minutes left in our class. And let's see, we've got one more force to worry about. Do you see that this link force is pushing the body B? So I've got to make that plus the force of the link equal the mass of the length times acceleration. Now I want you to stare at these two equations here. I'll box them up for you. I wish I had time to do the algebra, but I don't. My time is running out. But if you look here, there's two equations with two unknowns. So, but you see the acceleration's constant for both of them. They're connected. Whatever the acceleration of A is, it's connected to B. B has the same acceleration. So you have two equations with two unknowns. Is there anybody out there that can do two equations with two unknowns? You all can. So if I only had time, we would solve those two equations and two unknowns, but you could do that. And that's problem 13.5, and you'll get the answer in the back. Did that make sense to anybody? Probably not. It's sad, but our time together has come to an end. Was there any question from anybody? Well, enjoy that test. You've got till Wednesday at midnight. I know you'll do really good on it. Anybody else? Last comment. I wish we had time to do that algebra. Okay, well, I'm going to sign off. Goodbye, students, till Wednesday at what, 9:30? Somebody say bye.
Goodbye.
Goodbye. Bye-bye. See you later.